Hello, my name is Axel Marmoret and I'm a PhD student at ERISA in France. In this video, I am presenting a factorization technique called non-negative Tucker decomposition, which is based on tensor algebra. This method can be used to extract new representation of music signals and to uncover audio patterns in music pieces. In this work, we evaluate the potential of this technique for the task of structural segmentation of music in audio form. So now, let's consider the chromogram of a song. Here, the song Come Together by the Beatles. From this time-frequency representation, we can construct a third-order tensor, which we call the time-frequency bar tensor, or TFB tensor. This TFB tensor is obtained by estimating bars and slicing the chromogram on the downbeats, with a split time in two dimensions, a low-scale one, which is the relative time within bars, and a high-scale one, which is the bar index. We decompose this time-frequency bar tensor X using the non-negative Tucker decomposition model, or NTD. NTD provides a compressed representation of tensor X as three-factor matrices W, H, and Q, and a core tensor G, which combines the factor matrices so as to reconstruct X. Note that the dimensions of the factor matrices, also called ranks, are parameters that have to be set prior to the decomposition. NTD was first applied to music modeling by Smith and Goto in 2018. Here is a visual illustration of the way factor matrices W and H are combined via G. Each slice of G can be understood as a mixing matrix of columns of W and H. While W represents pitch class information, H can be viewed as a collection of rhythmic activation patterns at the inner bar time scale. Each combination of W and H via a given slice of G defines a musical pattern. The figure on this slide depicts a musical pattern on the left-hand side. Each slice of the core defines a musical pattern and is associated with a column in the third factor matrix Q. Each row of Q is associated with a bar in the time-frequency bar tensor. Hence, Q represents every bar of the music as a combination of musical patterns. You can see here the transpose of the matrix Q for the song Come Together. If Q is sparse, the NTD can be assumed to cluster similar bars into a common musical pattern. Thus, we assume that this representation is strongly correlated with the structure of the song. In order to evaluate the decomposition in the structural segmentation task, we compute barwise similarity coefficients via the autosimilarity of the transpose of Q. Here is a comparison of this autosimilarity, on the right, with the barwise autosimilarity matrix of the chromogram on the left. It is striking as the NTD-based representation exhibits a much more polarized distribution of the autosimilarity than the one based on the chromogram, and this is a consequence of the sparsity of Q. In our paper, a structural segmentation method using the NTD-based representation has been designed, tested, and compared to other state-of-the-art blind methods, that is, methods which do not require a set of training examples. In our experiments, our method outperforms conventional ones in the RWC-POP dataset. Additional results, reported in the paper but not on this slide, indicate that it could potentially be competitive with deep learning-based approaches. The whole code related to this work is open source and has been made accessible as this link to my GitLab. Feel free to navigate and explore it. In addition to the code itself, the folder contains Jupyter notebooks which details the segmentation algorithm, some settings, all the experimental results, and a walkthrough of the decomposition and segmentation processes. They are available in executable format for reproduction and HTML format if you only want to see the results. See the Reed-Lindman book for more information. Thank you for watching this video. Don't hesitate to contact us for more information or for potential collaboration.